Hi and welcome everyone. Tonight our goal is to program UPGMA, the evolutionary tree construction algorithm that we learned about previously, and along the way to learn a little bit more about object-oriented programming in Go to give us the tools that we'll need. So I'm going to cover the object-oriented programming topics first, and I've got a text editor open, and I'm just going to put a package main in there. And I'm going to save this as, it's a slow save, but I'm going to save this into Go SRC. And let's create, so we had, let's create a folder, something like OOP, all right, Object-Oriented Programming. And I'm going to call this main.go. All right, and so I'll have an import FMT statement and fun main. And I'm just going to say something like object-oriented programming in Go. Okay, I should say more object-oriented programming in Go since we've already learned a little bit about it. For now, I'm going to say here's what we would like to do for UPGMA. I would like to define my own type that is a tree type, and that has, so it's a tree object. And how I had presented this previously was to say, well, we could have a slice of nodes is what constitutes the tree. And another way of doing this is to say, well, actually, if the tree is just the slice of nodes, I could think of them as synonyms. And so I could say that a tree is just a slice of nodes. So every time I see tree, I can kind of do the replacement that it's a slice of nodes. So I could pick one of these two. If I really want to think about a tree as having a slice of nodes, then I could keep the former. All right, so I'll comment this out. And I could also have a type that's a node object. And what we wanted to do was to allow the node to have an age as a float 64, to have some label that would name the node, and to have two children, since this is going to be a tree that is a binary rooted tree. So we'll have a root node at the top, and then until we hit leaves, where every node is going to have, or every internal node I should say, is going to have two children. And so here's our data setup. I haven't used it at all yet, but I've defined my types, and I could cd into the directory that I'm interested in. And if I were to compile this, then I will get an immediate compiler error that says you have an invalid recursive type called node. And we've learned a little bit about recursive functions in the previous lecture. And so a recursive type is what it sounds like. It's a type that includes itself as a field. And so we see this is what we've done with node, is that we want this idea that a node will have two children. And so we've thought about a field as something that an object has, an attribute of that object, or something that it contains. And so if an attribute of the object node is that it will point to the two children, why not set the data up in this way? And why does Go give us a compiler error? The answer is that Go will try to, if you are going to declare a node, right? So say that in main we were to declare var v node, then Go would go ahead and kind of allocate memory for that node, and it would say, well, what are the fields of node of v? It needs to have an age, it needs to have a label, and it needs to have two children nodes as well. And so it would allocate memory for, with the default value of 0 for the age, a default empty string for the label, and for the children, what would it do? Well, it would need to create two nodes. And so it would go ahead and create those nodes. And what would be their age and label? Well, they'd get the default type, and each of those two nodes would get their own children nodes. And so you now have 4 nodes that got created, and each of those 4 nodes would get default age and label, and then they would have 2 of their own children, and so on. And there's no stopping this process. All right, so the way that Go manages memory would prevent you from setting something like this up, because if you can't have a recursive type in this language, because if you were to declare a variable of the node type, then you would get this infinite process of children being created. So it will not allow us to do this full stop. Fortunately, there's a workaround for it, and it's one that, having seen this, will make a lot of sense, I hope, but that I will come back to when it comes time to actually implement UPGMA. And so I will just comment this out for the moment, because it's not something that we're going to use. Okay. What we're going to cover in this file is a little bit more about object-oriented programming. And in particular, I would like to recall that when I introduced object-oriented programming, we talked about shape object types. So we had a rectangle object, we had a circle object, and we had a rectangle object. And the rectangle object had certain attributes. So it had a corner point. So we could say this is one corner of the rectangle. It had a width and a height, also as float 64. So I could put all of these on one line, but I like separating them in this way. And it also had a rotation parameter. That was a float 64 as well. That allowed us to rotate the rectangle. And then we had a circle object as well. And it had a center point. Okay, so in this case it was a corner point. And in this case it's the center point of the circle. And then I had a radius 2. So if I know the center point of the circle in two-dimensional space, and I know the radius, that's going to define the points that form the circle. And it doesn't matter how I rotate that, I'm going to get the same circle. So I might have a rotation just if I were wanting to be consistent here, but the rotation won't change the shape of the circle. So for our purposes here, I think it's fine to exclude it. Now, you might imagine, thinking back about our idea of abstraction as being important when we program, you might imagine putting something like an area field within a rectangle or an area field within the circle object as a field. But you would note that these are both inferable from the fields that we already have. All right. So there's a general principle here where you don't want to have too many fields. So there's no sense in adding a field if you can infer it or compute it easily from the fields that you already possess. And so in this case, we know what the area of a rectangle is. Okay, it's just the product of its width and its height. So we could return the product of r.width and r.height. We could do the same thing for the circle. So I could take a circle object. I want to return a float 64 corresponding to that area. And here we want to return, well, I want to import math.pi. It's a constant that comes from the math package. And it's pi r squared, if it's been a while since we had algebra long ago. So pi times c.radius times c.radius. And so we have the area of each of those. I don't know why I called it circle of circle. But we have the area of each of a rectangle and a circle. And now if I save this and compile it again, I'll get an unexpected type. Okay, I forgot to give the attributes there. I'll get the compiler error that I anticipated having to begin with, which is that area is redeclared in this block. So we have a good idea here, which is that why add something as a field if you can compute it quickly? And but there's a problem, which is Go is not going to allow us to name two functions that take two different types the same thing. And there's multiple workarounds to this. One way would be to really get into kind of level 3, or the next level of object-oriented programming, where we might want to define a shape, and we want to be able to say, well, a rectangle is a shape and a circle is a shape, and to be able to handle both of those cases. So to have one function that tries to compute the area of a shape, and maybe branches based off of which specific type that the shape is, And so we got hierarchies where a rectangle is a shape, and a square perhaps is a rectangle, and maybe you had a quadrilateral that's in between there, and a circle is technically an ellipse, and so you have this hierarchy of what types of shapes are which other types of shapes. That's one way for us to go about it. I don't want to go down that path because for this it's a nice way of illustrating a different feature that we have in Go, which is a method of an object. And so we'll be able to fix this if I simply say, well, it's beyond computing the area of a rectangle. We could have made it a field. And so really it's as much of an attribute as the width or the height. And so let's make this what is called a method of the rectangle. Okay, and so this looks like a minor change, but what it allows us to do is to call a function like this with, if we have a rectangle R, we can call the function with not area of R, where R would go in the parentheses, but R dot area, or C dot area. So we're really thinking of the function as being tied to the object, right? It's an attribute of the object, or it's an action that the object is taking. It still could take, we could put parameters inside of the parentheses if we needed to take additional input here, but the main input is the rectangle or the circle shape object, and so we're going to move it outside of the parameters of the function and put it before the function, and then the question would be, how would we call this? So the question of how to call is if I define a rectangle here and define a circle, and I'm not going to move them around much. I'm just going to set r.width equals 3.0, r.height is equal to 5.0, and c.radius is equal to 2.0, something like that. So we'll know that we'll have 4 pi as the area of C, and we know that the area of R is going to be 3 times 5, which is 15. Then I'm going to be able to print. I will call these with r.area. It's still a function, it's not a field, so I'm going to put parentheses there. That will give us the area of R. And you'll notice that as soon as I put the parentheses in it, it changes it from red to blue because Adam here, the text editor, is interpreting that as a field, just as radius, height, and width are, whereas if I put the parentheses, it knows to interpret that as a method. Or I should say Go does. So I'll save this, and now when we build, we shouldn't see any compiler errors. And when I run the program, which I had called OOP, we're going to see the area of R printed as 15, and then 4 pi, 12.566, etc., is the area of C. All right. So a rapid introduction to methods. And so we have kind of a bird's eye view of what object-oriented programming is, where you have objects, and then the objects can have fields, which are properties. So if you think of an object as like a noun, you have the fields are almost like the adjectives, the descriptors of the object. Although sometimes you hear, right, you have a description of an object, which is its area. But the methods can also be, do some procedure or function as well. So if we wanted to, say, move the rectangle, then we could write a function that might, say, translate a rectangle or translate a circle. And so we could have something like a function called rRectangle, translate the rectangle. And say we want to move the rectangle by A units in the X direction and B units in the Y direction. Okay. Then, again, abstraction is powerful here because if I'm imagining the rectangle or a circle as existing on a canvas or in some space, in two-dimensional space, then if I want to translate the rectangle, say, 2 units to the right and 1 unit down, then whatever my special corner point is, it suffices to just move that corner 2 units to the right and 1 unit down. So in this sense, then, you might imagine, well, let's look at r.x1, and let's add a to it, and let's look at r.y1, and let's add b to it. So if I simply add a to the x1 corner, I should say the x coordinate of the corner point, and then add b to the y coordinate of the corner point. I want to be just completely precise about what I'm doing here. All right, and the same thing would apply for a function, say, the circle, and I want to translate it. So here's, again, an example of a method. It is a method of the rectangle, but it also needs to take some parameters, so we plug those into the parentheses too. And for the circle, we can translate the circle if we simply do the same thing. So we have a center point of the circle, which has coordinates x1 and y1. We're going to add a to x1, and we're going to add b to y1. And that should translate the circle. So we can save this, and we should be able to, after we've printed the area, let's translate the rectangle and the circle. And so we know what x1 and y1 of r dot of r and c are, but I'll print this just to convince us that if we compile and run, we're going to see those two areas that we printed, and then we're going to see 0, 0, and 0, 0. So we have a rectangle with a corner point at 0, 0, and we have a circle with a center point at 0, 0. And so let's move these. So let's call r.translate of, I said 1, -2, and let's call c.translate of -3, 16. Okay, and because we started at 0, 0, that would, in theory, move the corner point of the rectangle to 1, -2, and the center point of the circle to -3, 16. And so now if we print the coordinates again, I'm going to be lazy and just copy both of these statements, as opposed to retyping all that. We should see 1, -2, and -3, 16 printed after we compile and run. Or at least we would hope so. But that's not what we see. We see that the new coordinates are 0, 0, and 0, 0. So it appears here that nothing is actually happening when we do the translate. And we know why this is the case. Or we already have enough knowledge to appreciate kind of what happens here. And it's the same thing that what would happen if I plugged R or plugged C as parameters into the translate function, where we already know kind of what the scope, going back in time, we know what the scope of a variable is. And that's the lifespan of the variable. In particular, we know what the scope of a parameter of a function is. Typically, it lasts from the beginning of the function to the end. So a and b, for example, if I pass them in, these temporary variables are created, a and b. They're used throughout the course of the function, and then they're destroyed at the end of the function. The same thing goes for the rectangles r and c. So I've created my rectangles in main, or my rectangle and my circle in main. When I call the methods translate on the rectangle r and the circle c, a copy of those is created. And so currently, that copy is what gets updated here, and then at the end of the function, the copy is destroyed, and I didn't change my original object. All right, this is going back in time. It's the exact same principle that we saw if you had x as an integer or something, and you plug it into a function and you change x. Well, that doesn't affect anything if you have a separate, say, y that you plug into that function. Y will remain the same outside of the function because of variable scope. So this is a good thing. It just means that we need to figure out how to actually move the object that we have. And the natural thing to do here, I guess, in terms of what we currently know, would be to change these functions to say, okay, well, if I want my r and c to be updated to whatever it is that goes on inside of this function, I could set r equal to r.translate and c equal to c.translate. And so in each of these functions, I could return excuse me, return the, I'm getting ahead of myself, return the object type that we're interested in. So the copy would get created, but then that copy would get returned, and so we would essentially move over the copy into whatever variable that we set equal to the rectangle or the circle. And so if we return each of these objects, now if I call these functions r equals r.translate, because the copy is returned, r will be updated, and because the copy of c is returned, c will be updated here. And so now if I save, compile, and run, then we're going to see that indeed we're now changing the corner point of r to 1, -2, and the corner point of c to -316. That will fix the problem, but it is very wasteful of memory because the entire rectangle winds up getting copied. We create this new circle object or a new rectangle object that when we call c.translate or r.translate, whatever rectangle or circle that we're working with gets copied over, and so we have a new copy of it, and then that copy gets set equal to the variable outside. That's what this copy gets returned. So, you know, we create two things that have the same values in order to just throw one out and update this one to whatever this has, which doesn't seem like a grave offense. After all, they're just a rectangle or a circle. But if you think about as we move towards more scalable programming, and you have, say, for example, you want to build a video game, the last thing you want to do is just for a character to say, you know, move their arm toward another character. You don't want to duplicate everything in the environment or have to duplicate an entire character that has all these different attributes just in order to make a small change to it. All right. And so as a result, we would like to be able to, if I want to translate a rectangle, let's not copy the entire rectangle. If I want to call a method on an object, maybe I don't want to copy that entire object. I just want to access the object and change it. All right. And so how we're going to get at this in Go is to think a little bit more about how memory works and how Go will interact with the memory in the computer. And so your computer, your laptop may have a certain number of gigabytes of RAM. The computer I'm recording this on has 16 gigabytes of RAM at the current time. And you can think of the RAM itself as a big memory storage facility that you can use for your programs. All right, and it's a reasonable metaphor because if you have variables or whatever you're storing in the RAM, you'll even have them divided into addresses. Okay, and so there's a symphony that goes on when you run a program in order to store objects or variables or arrays or whatever you're working with in the RAM and get this kind of going back and forth. But we won't cover that. That could be an entire very deep course in terms of how that symphony is orchestrated. I just want us to think about the abstraction of the memory as a storage facility and to take a slight detour that will prove really valuable in understanding how we get around the issue of duplicating memory or duplicating objects when we don't need to. And so what we're going to look at is something called a pointer. And I'm going to keep this on hold for now. So that was kind of part one. Part two is I'm going to have a discussion of pointers. All right. And what is a pointer? A pointer is a variable that holds the memory address of some other variable in the simplest sense. So a pointer in the simplest sense is just, think of it as a memory address. So in that sense, it's just a number, right? It's a location of knowing where something is stored. And so, for example, if we look at what the simplest type of thing we could do, we could declare an integer and set it equal to our favorite number, okay? And that variable b exists somewhere within the memory, and it's going to vary based off of what other computational resources you're using at the current time, your operating system, the specific make. All this will affect exactly where that variable gets stored. one of the wonderful things about programming languages is that we don't necessarily need to care how that process happens as long as it happens reliably. And so, but it is going to be helpful for us to know, all right, I declared a variable, so go where did you put it within my memory? And so I will have a pointer variable. So if I want to say that a is a pointer to an integer, so we have the type here is important. This says a is a pointer to an integer variable. Go is very type specific, so it's not going to allow a to point to anything other than an integer. So a will be the pointer, i.e. the address. Okay, so it's a pointer to, or the address of, some integer variable. That's all it is right now, and it hasn't been really set to anything. So if I were to print b and print a, then what we would see is the last two lines of what gets printed, which is -47 and the special value nil. In fact, I'm going to comment out everything else that we did in part 1. Part 1 could be called Introduction to Methods. And so I'll comment out what's contained in part 1, just so when I do these prints, you're going to see just what we are interested in. All right. So we say, yay, more object-oriented programming in Go, but then we have the value of b, -47, and the value of a. So a currently has the default special value nil. All right, meaning that it does have a type as a pointer to an integer, but we haven't set the address yet. So it doesn't store the address really of anything. And so if we want to say, all right, well, where is b stored in the RAM? Then we could say, let's set a. It's going to point at an integer. So I mean, it's going to reference where an integer is stored. And we're going to use the special symbol ampersand. So Shift 7 on my keyboard. And we're going to say ampersand means location of. So we have set b equal to some integer. It gets created somewhere. We create a as a pointer to an integer, so it's still a variable, but it just has this default value equal to nil. And then now we have set it equal to the location of b. And so if we print a, we won't see nil anymore. What we'll see is the address of b. Here it is. Okay. And I would very seriously doubt that if you run this on your own machine that you would see the same address that I am seeing here. The one thing that you will see, most likely, is, I didn't mean to copy that. One thing that you will see most likely is the 0x at the start. All right. And so the 0x indicates that everything that follows should be read as what's called a hexadecimal number. So we think of, or the hexadecimal representation of a number. We think of numbers in terms of base 10. So we have a ones digit and a tens digit and a hundreds digit and a thousands digit and so on. Those are all shared as, we have a ones digit, so that's 10 to the 0 and 10 to the 1, and then we have 10 squared and 10 cubed, etc. But you could also represent numbers via any other base. And so if you were going to represent them in base 16, which is what hexadecimal is, then you need the digits 0 up through 9, but you'd also need, so that would give you 10 digits, but you would need 16, so you would need A, B, C, D, E, F, corresponding to A being 10, B being 11, C being 12, D being 13, E being 14, and F being 15. And so if you think about counting, you would count 0 up to F, and you'd be at what we think of as 15. And then when you went to 16, just as when you count 0 up to 9 and then you hit 10, it's a 1, 0. The same thing would happen in base 16, so you have a 1, 0, meaning 1 factor of 16 to the 1, and then 0 factors of 16 to the 0. So that's the number 16. It's just 1 0 in base 16, or hexadecimal. And each of those digits corresponds to a different power. So we would have in this case, you would have 18 times 1. You have 0 times 16 to the 1, 0 times 16 squared. C, remember we said that's 12 times 16 cubed. And then we would have 7 times 16 to the 4th, 5, 6, 7, 8. And then I think I've got this right. We would have another 12 times 16 to the 9th. And if you add up all of those, then that would tell you what address that you're presently pointing to. So that's the location of B in the memory. So that's, memory addresses are represented in base 16. The reasons are mathematical for that. It's because it's a simplified representation of base 2, where we need 4 times as few digits, and everything that happens in a computer is actually done for the essentially in base 2 arithmetic, which is just where we have the digits 0 and 1. And that's all I'll say in terms of base 2 and hexadecimal notation. There's a lot more to say there, but I at least wanted it to be clear that this is just a number. All right, it's a 0x. Interpret what comes afterwards as a hexadecimal number so that you're not weirded out when you see a C or an F or something like that, but it is just a memory address. All right. Now, the question becomes how to use this for our purposes. Remember, what we wanted was a function that didn't necessarily create a copy of some object. So we can, just as we have a pointer to an integer, we can have a pointer to an object too. So if I were to create a variable C that's a circle object, and I could create a pointer to C that's a star circle, all right. Now, just in the same sense, I have not set it equal to something. It will have the value nil currently. And I should point out as well, is there a one line A colon equal ampersand B? Yes. So just as we can set an integer n colon equal to 3, or a string s colon equal to the string hello, we can also set A colon equal to ampersand B if we have an integer B, and Go will interpret that as, okay, B is an integer, you're declaring a variable that is equal to the location of B, so the type of A has to be a pointer to an integer, and that's fine, and that's what you would probably use most of the time in practice. But I want to show that how this works is you have a special type for each type. You have a pointer to that type, and you can declare a pointer variable just as you did before. So everything here is consistent in terms of how variables are declared. Returning to the circle example, we have a variable called C that's a circle, and then we have a pointer to C that's a pointer to a circle type. It currently still has this special value nil. It doesn't matter whether you have a pointer to an integer or a pointer to a circle. If you have not updated the address of a pointer, it will have the value nil. And if you wanted to point it, we'll make this a little bit shorter. Pointer is equal to the location of C, for example. All right, so now pointer points to C. Okay, somehow a pointer isn't necessarily isn't a keyword, as you can see, because it's not colored in a different color. Maybe not the best variable name, because you don't want to use every pointer that you have is called pointer. But anyway, we have now pointed it to C. And so the question that I have is, okay, if we just have a pointer to an object, can we change it? Okay, and this is almost a philosophical question, which is, if you think about, if I know where something is stored, can I go in and access it, right? Yeah, I mean, if there's a key to the storage facility, then it's a different story. But in our thinking of this, if I know where a variable is being stored, then I can simply go into that location in the memory and look inside of it and rummage around and change its fields. All right, so knowing where something is stored is just as good as having the name of the variable itself. And so the answer is yes. And if I want to access, say, the fields, so I've declared the variable circle, so it has the default values. So say we want to change the radius of C, okay? Well, let's just make this a little wider so you can see it. By accessing the pointer. So the easy way to do it is, of course, to just say c.radius. Okay, equal to our favorite integer. But I can actually change the radius with pointer. And the classic way of doing this is what's called dereferencing the pointer. So the pointer is currently a star circle type, which means that if I have the pointer, there are other languages where if I were to try and do something like pointer.radius and set this equal to 4.6, then the language would complain. It would say, well, yes, this is the attribute of a circle, but you don't have a circle. You've given me a pointer to a circle, which is a different type. It is a type star circle. And so what you have to do is, yes, you have the address, but you need to tell me, I don't care about the address, I care about the circle that's contained at that address. And so we would need a separate way of accessing it. And so the way we would do that would be to use the star. So star has two meanings here. So star also means, allows what's called dereference of a pointer. It means grab the variable at the address that the pointer points to or refers to. So you see why it's called dereference, because a pointer refers to an address or the address of some other variable. And so if we're not interested in the pointer but the thing that's being referenced, then you dereference it by using this star. And so now if I star pointer, Go understands to go into whatever the address that is contained at pointer, access the variable that's within it, and now change its radius field to 4.6. So we'll be able to see if I print c.radius. Remember, c is the circle object. So let's see what happens if I compile and run that. Now you'll see that the last line is indeed 4.6, so it works. All right. The good news is that you should understand this. You should appreciate that pointers are valuable because they allow us to know where something is stored. So that's one reason why they're very valuable. You'll see another reason shortly. But there's a piece of good news about how Go implements this, which is that you should understand that a pointer is different from the variable that's contained in the address that the pointer points to. One is an address and the other is a variable that's contained within it. But the good news is that Go will automatically interpret a pointer to an object as the object. So with beginners, when you have dereference, this is like the big barrier often for introductory programmers, where you have to keep juggling back and forth. Do I have the object or do I have the pointer to the object? And I need to make sure that I dereference, that kind of thing. Go doesn't need dereference. So in another language that implements pointers, if I wanted to change the radius to 2.33, it would get angry. You could imagine a compiler error where it says pointer is a pointer type. It doesn't have a radius attribute. But this is fine. Okay? And so Go will interpret this as, yes, you told me it was the pointer's radius, but I understand. I'm going to go in and look at the memory address and change the radius of whatever is stored there. So now if I print c.radius and compile and run, then we'll see 2.33. Okay? So it does indeed go in and change that object. And this is why it will be helpful to change the fields inside of a method. So before, what is the applied practical purpose of discussing pointers in this sense? Well, one, you get a little bit of a sense of memory management. that's going on. But secondly, we can come back to the functions that we wrote, all right, where we had a rectangle translate function and a circle translate function, and all we could do was to duplicate the entire rectangle, change that duplicated rectangle, and then return it, or do the same thing with the circle. And now I'm going to write translate two functions. That's not ideal, but just so that I'll have both functions present here. Okay, if I change this to not r rectangle, but r pointer to a rectangle. Remember, if I put star before a variable name, that means dereference it. It means if I put the star here, that would mean that r is a pointer and go in and access the variable that's contained there. But if I put it before a type, then the star means pointer to. All right. So rather than have, if I tell go r rectangle, then it's going to say, all right, you told me I need to duplicate whatever rectangle object that you give me, and it may get destroyed at the end. Whereas if you tell go r star rectangle, it says, okay, I have a pointer to the rectangle, which means that what you're going to give me as part of the method is a reference to a specific rectangle, and I'm going to go in and I'm going to update that specific rectangle, and we'll see how this works. So no duplication will happen in that case, and the functions are the same. I don't need to return anything because technically, again, if we were working in a strict language with respect to pointers, then if it's a pointer to a rectangle, if that's what r is, then I would technically need to dereference r in order to access the field of the rectangle that r points to. And I would need to do the same thing here. But as I pointed out, if you haven't pointed out, I'm getting punny here. But as I mentioned, if you have a pointer to a rectangle, then that's good enough for changing the fields. So in practice, what you'll see is just, we'll probably use, is just r.x1 and r.y1 in Go. And this will become much more comfortable because you have to understand that you have two understandings of what's going on here. You have, yes, we can dig into the details of what pointers are, that they're addresses, how to work with them, how to dereference them, and so on. But you also have, from a practical perspective, you just realize that if I see no star here, then that means that I'm going to create a copy of the object. Whereas if I see a star here, then that means that I'm going to get access to whatever I'm calling. So if I have r translate to AB, and let's write, I'm going to have a circle translate to function. I'm not going to return anything. So don't need to return anything in either case, but I'm going to have a star circle. All right. So I'm going to change whatever the pointer, whatever the circle is that C points to, I'm going to change its x1 and y1 fields inside like that. Now let's see what happens if I, okay, technically I would need to, let's say, do, I have a pointer to C. So pointer points to a circle C. Let's call that translate to. And let's move it to 4.3, negative 0.71. Okay. And now let's print C.x1, C.y1, because I have the pointer, which is referring to the memory address of C. And now when I call translate to, it should go in and change that behind the scenes since I'm referring to C. And now when I print C.x1 and C.y1, I should see that the x1 and y1 values have changed. Okay, which is what we see. That's the last thing that we print. And so after we've translated the circle, then we will have changed that actual circle. All right. So you have a couple of different senses here. A pointer is, in a sense, just an integer value since it's referring to a location in the memory. But it's also like a bookmark, right? Because if you have a pointer to an object, then if you pass that pointer into a function, then you're going to have whatever that value is still going to refer to the object. So it allows you to control an object from within a function in this way. All right. So yes, the rectangle is nowhere to be seen. All I have is the pointer to the rectangle, but Go will allow me to edit the rectangle here or edit the circle here because I know where it is stored. All right. So again, two different senses. It's just a memory address, yes, but it's also a bookmark that allows us to go in and edit something. All right. So one more thing here, which is this is the very formal way of doing it. And in practice, if I wanted to call translate to, some languages would say, well, you need to give me a pointer to a circle because it's func C star circle. So pointer has to have type star circle, which it does. Go will have another little shortcut which says if I just call C.translate to, it will understand. So Go will understand to access C, not a copy of it. Okay, so that the difference again between a function C circle and a function C star circle on a high level just means with func C circle you create a copy, with func C star circle you do not, you access whatever is you're referring to. All right, so this will be okay, and we won't get, for example, a compiler error because C has type circle and translate to is expecting star circle. Go understands what we want, and it will make this translation. And we're going to see that, you know, after the translation happens, a copy wasn't created as it was before, and so the circle was indeed moved. One more thing here. So before we come back to UPGMA, I'm just going to make a review that we've seen this a little bit before. So you didn't know that we've worked with pointers before in Go, but we have. And the reason why is because you've seen functions already, or certain types, that when you plug them into a function, that you actually can change whatever that type is. Whatever your variable is, you have access to it. And that occurred when we had functions. I'm just going to put them beneath now. So if I had a change first, and I took a slice, say a list of integers, and I didn't return anything, but I just said list of 0 is equal to 1. So I changed the initial element to be equal to 1. And I'm in fact going to comment out what we've done here in part 2 as well. So comment that out. And then part 3 will be a bit about slices. So I will have a change first function that takes a slice of integers. So let me create a list, or I can call it something different. A colon equal to make, let's just make a short slice of integers of length 5. And so this will be, you know, 0, 0, 0, 0, 0, since we have a length 5 slice with the default value of an integer, which is 0. And so now if I call change first of A, right, well, we've seen before that if I were to then print A, when we compile and run, you will see that A actually gets changed. So the typical behavior of a function is that if you simply pass something into the function, then then something changes along the way. Well, a copy is created, so the change only happens to the copy, and then the copy is destroyed. That doesn't happen with slices. So we've seen with slices, if you create a slice, you get access to the actual slice. All right, and now we understand what is going on, or we maybe have an inkling about it, which is that a slice is a pointer to an array. It's a little bit more than that. It has a length, I'll say along with a length. All right, so it will tell you how long the slice is as well. So when we say make a slice have length 5, well, we know that the length of the slice has 5 elements. But on the higher scale of looking at this, we think, well, a slice is just a pointer to an array. So if you have a pointer to an object, you pass it into a function or call a method on it, then you change the object. This is different from change first array, where you have, say, a list of just 5 integers, and here you have list of 0 is equal to 1. And so if I instead said b, var b is an array of length 5 of integers, and if I were to change first array of b, and now we're to print b, a copy of b was created. Okay, so the entire array gets copied over. This is partly why we use slices, so that you don't have functions that constantly, every time you call the function and you have an array, say is a big table, it's got 10,000 elements in it. And every time you want to edit one element and you call some function, then it duplicates that entire array over and over again. This becomes very wasteful of memory, and there's no reason to do it if we want to just edit elements of an array with a function. So this kind of explains the difference between slices and pointers in this sense. In particular, if I let me save what I've done, compile and run, then you're going to see that for the slice, we changed that initial element. Even though it appears that it's just being changed inside the function, it's actually being changed outside. So we're passing in a pointer to some array. Whereas if I have the array itself, then the entire copy of that array is created. And so that copy winds up being destroyed. Okay, so whatever list is here gets destroyed because the function ends. And so yes, that list initial element got changed, but if I have b and it's an array of integers, b, just a copy of b is created, and that's what list is, and so you won't see any change here. So it's a critical difference here between arrays and slices. So if we think of an array as a slice as a pointer to an array, there are a few more kind of, I don't know, dirty details that I think you could have learned earlier in terms of Go, but that now will make a lot more sense. So for example, if I were going to make C be a slice of length 5, you might see this third parameter when you make an array or make a slice. So C is a slice of length 5 that points to the first 5 elements of some array of length 10. And why might you do this? You might do this if you might want to create a big table of data, but then you're only actually interested in, at least at the start, whatever the first few elements are of them. And so I only want to refer to these first few elements, but I want to allow myself to grow the amount of data that I'm putting into that array behind the scenes. And so this would be like a hyper memory efficient way of doing it. You could, so C is a pointer. It creates the array of length 10, and then it points to the first 5 elements that are there. This is, again, shorthand. You know, we have a var C slice int, but this is a one-line declaration. And then we could also put some values into this. So we could fill up, if I want to range over C and set C of I is equal to, equal to whatever your favorite value is. I'm just going to give it something, okay? And now you might imagine that something like var D is a slice of integers, and it points to C of 3 to 7, okay? Well, C only has length 5. You might imagine that would give us some kind of runtime error, but that's actually okay. So if I were to build this and run it, let me show you what C and D are. And put that comma there. All right. So what are C and D? If I compile after saving and run, then the last two things that get printed are that C is 3, -3, -1, 1, 3, 5. Those are those 5 elements that I set. So I ranged over C, which means it's going to range over those 5 elements, and it's going to set the elements. It's not going to do anything else. If I set D to be a slice of integers, so it's itself a slice, and what is it going to point to? It's going to point to everything from the 3rd element of C up to, but not including the 7th, or element 7, element at index 7 of C. So the subarray of C, starting at position 3 of length 7 minus 3, which is 4. So you've got this variable D, and it's out of range for C, but Go will know to go in, and if the array behind the scenes, remember I created an array behind the scenes with 10 elements, so the question is, what happens to the other ones? This sets the first 5 elements of the array. Remaining 5 are 0, and you're starting to see them, okay? So in particular, I could go all the way to 10. And you'll see all of them. So here are the elements of C, -3, -1, 1, 3, 5. Here are the elements of D. You have 3, 5, so that's those 2 elements. That's the element at index 3, 0, 1, 2, 3 of C. And then here you have 3, 5, and then those 5 default zeros. If I were to put 11 there, that's where I get into trouble, because I've gone past the size of the array that I created. Remember, I created an array of length 10. So now I'm size bounds out of range. And so we still need to understand, how big that will be. So I'm going to go back to my previous example. And now, I can visualize how this is happening. I have the first 5 elements, and C is a pointer to the initial element, and it knows to have length 5. And D is a pointer to the element at index 3, and then it says, look at 4 total elements. So it's a pointer plus the length. All right. And you could say, well, if they're both pointing to the same underlying array, right, C and D both point to the same array. So it's possible now to update one and it changed the other. All right. So for example, what if I were to set D of 0 is equal to, I'm going to give a special value so you'll see it, 1820. And so now if I print C and D, then I'm going to see that the element at index 3, so here was the original values of C and D that we had set. Now when I update the 0th value of D, you'll see that gets updated. Before it was a 3 there. But it also, because it's changing the array behind the scenes, now C will change too. That's not necessarily bad behavior. It allows you to, say, create one table and have a lot of different things referring to that same array of data. But it's worth knowing kind of how this works, and there are particular applications where you might use that. Okay, and there's more to consider here too in terms of the indexing. But like for example, you might say, well, does this mean that I can access something like C of 6, right? And if I try that, I'm going to get a runtime error. I'm out of range. So if you have a slice, remember, the slice is a pointer to the array and then the appropriate length. So if I'm trying to create a subslice, Go will interpret that and understand what I mean, that I want to go out of bounds. But if I'm just trying to say set something, right, if I wanted, or if I said C of 6 is equal to 12, it would get angry at me here too. So in the same case, I'm still going to get a runtime error, index out of range. So it wants me to understand and know how long C is, so that in a case like this, I'm not changing something that's outside of the bounds of what I had initially said C was. All right, and that would protect your data a little bit. Okay, so let me do one more thing then. Let me create, so we have a change first and a change first array function. I'm going to write one more, and that function is called delete. So let's take a list of elements, or an array of elements, so I should say slice of integers, and let's take an index that's a specific index, and I'll say delete removes the element of a given slice of integers at a given index. And this can be done with append. And so you might think, well, the natural way to do this is to simply say list is equal to append. I want to go everything up to the given index, and then I want to append, so I want to take that subslice. I don't want to include the given index, and then I want to append everything that's past it to that. And so how we do this is just let's take the subslice of list up to but not including index. Remember, that's our notation. And go, and we have let's append everything starting past the index up to the end. Then we're going to have 3 dots to indicate that we're appending potentially multiple things. So since we're appending a subslice, we put those 3 dots. And now we think, okay, that's a nice short delete function. We could perhaps put it in some basic package and import that whenever we like. And let's see what happens when we call it. All right, so this would be bad. Let's get rid then. Let's throw out C of 3. Okay, so I could set index is equal to 3. And now let's delete from C the element at index 3. And let's see what happens when I print C. All right, if I think about what C currently is, it's this slice that's -3, -1, 1, 18, 20, and 5. So you might imagine I've deleted that index of the element of the slice. I'm going to throw out the 1820 since that's at element 3 or index 3 of this slice, and I'm going to be left with 4 elements: -3, -1, 1, and 5. So let's see what happens. Okay, I should say C is. Just make this even clearer. And we get something truly bizarre. All right, you can see that we have -3, -1, 1, 3, 5, and then 5 zeros. So that's the array behind the scenes. C got updated, and you can see it's -3, -1, 1, 18, 25, and then 5 zeros. And after I call this delete function on C, I get -3, -1, 1, 5, 5. So I've duplicated the 5, and to that, but I've also gotten rid of the 1820. So it looks like that what was supposed to happen worked, but why is this extra 5 hanging around there? And so you can even see it's still lurking. If we look at D, okay, you've doubled the number of 5s there too. So for some reason, we're copying this 5 over. And so if we think about why this might be the case, when you call delete, and this is like a big brain teaser to really fully understand pointers. So if it's not immediately clear, that's fine, because it can be a tricky one to get your head around in terms of what happens. So when I call delete and I call it on C, remember that C is a pointer, but it's also a length. And so the value of C gets passed into this function, and it has C. So C was a bookmark to some location in the underlying array. So it says C is telling you to look at this location, but it also has a given length, all right, which is 5. When you pass it into this function, technically a copy is created, and it's a copy of the pointer. So C has this bookmark value, list now has this bookmark value, and they both are pointing to the same element here. All right, now if you're dealing with a circle, just as a pause here, if you're dealing with like a circle or a rectangle or some other object like that, and you're changing the fields, then it doesn't matter that you create a copy of the memory address, because if you go in and you change the object that's in there, it doesn't matter what does it, whether it's the original pointer or the copy of the pointer that does the actual access. Okay. In this case, it's a little bit different, because when you pass in the pointer C, the copy gets created. So now list points at the same location of the array, and it says it has length 5. But now list is the thing that gets appended to. So sorry this doesn't wind up on one line, but list is the thing that changes. Right? What does it change to? Well, it points at the same place as C did. It removes the element, and it, at the given index, and it gets updated to have length 4. All right, that's what happens when this goes behind the scenes. But notice, it's not a list is a slice, right? Why doesn't append work like this? And it's the same reason, because you need to set, after this process happens, you update what you're interested in. So here you update list, right? And so unfortunately though, list gets destroyed. Okay, and meanwhile, back up here, C is still pointing at the same place with length equal to 5. We haven't updated anything about C. It points at the same spot, and the append step has happened behind the scenes, but unfortunately, because a copy of C was created, it's the copy that now has length 4, and list gets destroyed, so that length parameter gets thrown out with it. This is not a hard fix. This is why it's list equals append list. If you're really making a change, it's C equals delete C index. And so all we need to do in this case is return the slice that we're interested in. So if we return list, then list actually still gets destroyed, but it will updates the slice outside of the function to have the appropriate length. Okay, so that now if I call what I did before and say what happened to C, did I really delete this element? So what I want is to see that C is -3, -1, 1, and 5. To delete the element at index 3. Then when we run this, we see that C is -3, -1, 1, 5. That's great. D, unfortunately, still has this duplication happen. All right, so in other words, D still has length 4. And when we did this append, we simply moved the elements over. So I've got another 5 that is still hanging out there. It doesn't appear in C, but that's the original 5 that we had in our matrix. It's the one that occurred here. So when I did this append, I moved that 5 over, but I didn't actually get rid of it in the matrix behind the scenes. So if you want a brain teaser, that's where I would leave this. How do I get rid of the additional 5 that is contained within D? Okay, and that would be something for you to think about as kind of a challenge exercise. All right, that was a lengthy introduction to methods and pointers in Go, but I think it's one that can be very helpful for understanding not just how Go handles this, but how memory management or in programming languages can work in general. And in particular, it will help us come back to implement UPGMA, because when we started this, we had what we wanted to do, and what I had discussed on a pseudocode level was that we would have a type that is a tree that simply contains a slice of nodes, and we would have a node struct that has an age attribute, a label field, and that would have 2 children. So it would have 2 nodes contained within it. And I use the term point there as well, because one way in which we can think of a pointer is as a edge or an arrow in a network. So if I'm an object and I point at another object, then I can go in and access that object anytime I like. So a pointer, if I know the location of that object, I can almost think of this as a connection from here to here. If I'm, if I'm at object X and I point to Y, then you could think of that as a direction from X to Y. If Y doesn't point at X, then that direction is just a one-way direction. So if I'm at Y and I don't know a pointer to X, I can't go in and access X, but if I'm at X, I can go in and access exactly where Y is. All right. So it's this one-directional relationship. And here, I can make a very small change to this with making the children pointers to nodes instead of node objects themselves. All right. So by making them pointers, we achieve something that's much nicer. We avoid the recursive type, because if you declare a node, say var x node, then the age gets set to 0, the label gets set to the empty string, and what happens to x.child1 and x.child2? So, well, if I were to say with var x node, x.age equals 0, x.label equals the empty string, and x.child1 and x.child2 are both equal to the special pointer value nil, which means they have not been set to equal the address of something. We can set them if you create two more nodes and I want to point x to its children. Well, I'll say x.child1 is equal to ampersand whatever that child is, and x.child2 equals ampersand whatever the other node is. But this doesn't create a recursive, infinite creation of data or of memory behind the scenes or allocation of memory, because x.child1 and x.child2, if I declare a node, they're both just going to get started off as the special value nil, and everything is fine. That process will terminate there. All right. So we'll have a really nice way of working around this. That would be what you would do in practice often whenever you have an edge that's a one-way connection in a network. Just make it a pointer to that object, right? And so you'll be able to go from a given node x to its children once they get set by accessing x.child1 and x.child2. All right. So I'd like to pause just for a little bit there and say, in terms of the object-oriented stuff that we want to discuss, that's the end of this part of this lecture. And in the next part, we're going to come back and implement UPGMA. I'll try to move through it reasonably quickly and build an evolutionary tree algorithm from a distance matrix. So that's what we're going to do here in part 2. I'll take, in the meantime, a brief break. If you're interested in joining us for UPGMA, we have the UPGMA starter code that I've provided, and if you look at the folder, then you'll notice that there are three different data sets. So we have a couple of small matrices, and then you have one that I've produced behind the scenes from a collection of ebolaviruses, where they're they're produced from the same gene in multiple different ebolaviruses from different human outbreaks, including the one that was isolated in the 2014 outbreak of Ebola in West Africa. And we also have two files here that I've provided. So we have a main.go, and we have an io.go. And let me close a previous work. And in the meantime, I'm going to CD away from the object-oriented folder and into this UPGMA folder. And let's take a quick look at what's contained here. So in main.go, I have a few type declarations. I have no actual code in main, and I have a bunch of function comments that will kind of illustrate the different subroutines that we're going to need and keep everything organized for us. All right, so nothing has been written here, but this is just going to prevent me from having to type a bunch of function comments. And then within io.go, this is just an input-output. So we have a function that reads a matrix from a file. Okay, so it's going to take a file name like, let me look at test data set small 1. Okay, it will take a file such as this, and it contains the number of species or taxa that we're considering, and then it's going to have the name of each one and then the distance matrix. In the remaining elements of that row, separated by tabs, same thing here that you see for test data set small 2, and ebolavirus matrix is going to be in the same format. All right, so you have a name. Here you have the question mark ebolavirus that we don't know where it goes. You could probably look at this distance matrix and see that we'll be able to get an answer for where it came from or what it's similar to. But let's go through the process. I mean, we might have an example where this is trickier for sure. And we'll go through the process of showing how we can produce an evolutionary tree. So that's reading in a matrix from a file. I've done that already, so this is just standard input, output, and go. So this scans through the file and creates two things. It's going to create a distance matrix, and distance matrix is just going to be a two-dimensional slice of FLT64s. So if you look at main.go, I have a type distance matrix as a 2D slice of FLT64s. That's just going to allow me to type distance matrix instead of this thing. All right, so it's the same type of thing that we saw before with cellular automata. And then at the end, it's going to return the matrix, so 2D slice of FLT64s, as well as just a slice of strings after I parse out the names of everything that's contained in that distance matrix file. All right, so that's read matrix from file. I can pull in from a file, and then if I want to look, like write out to a file, or in particular visualize the tree that we produce, there are many, many different ways of doing this. Okay, and I could write it to a file, or I'm just going to print it to the console, but we could just as easily take a file name out and do the output to print to the file. But it will print in one of a variety of different formats for networks. So if I want to print, every software package will have perhaps its own format for how it needs to read in a network and then visualize it for us. All right. I want to focus on this at the end because you'll see the format when we do it on a real example. And then I'm going to put it into the browser into essentially what's the simplest graph or network visualization package that we could use. The simplest software is probably GraphViz. It's an old piece of software. It's actually relatively fast because it doesn't try and add a bunch of features to what you do. So you can still generate pretty large graphs with it. But this will just prevent us from having to deal with visualization as a big part of what we do. I'm just going to have a simple print graph viz function that will print out the graph into a nice, or print out the tree into a nice format for us that's easy for me to just copy in the browser at the end. And it allows me to focus on what I want to focus on, which is implementation of UPGMA, using what we've learned about object-oriented programming in Go. And so we have a type that's a distance matrix. I'm going to think of a tree as just a slice of nodes, in particular a slice of node pointers. I'll do this because I'm going to create the nodes behind the scenes, and then everything that we do in terms of working with the nodes is just going to be as pointers. So I know that I'm not going to be duplicating nodes. I'm going to create the nodes exactly once. So if I want n nodes, I'm going to create n nodes exactly once, and then I'm just going to have pointers to those nodes, and I know that I'm not going to duplicate any node that I've already created. So what is a node? It's an age, I'll label as a string, and then, as I said before, it has 2 pointers to its children. So if we're at a node, we'll be able to access the children. We won't be able to access the parent. We could add that to our implementation. So I could be at a node and I could also know what my parent is. If I'm at the root, I wouldn't have a parent, so it would be nil. And that would allow me to go in either direction. And that's a different way of doing this. You would be adding more information to the node. So you could possibly also be incurring a bug. Like imagine if you point x at y and say y is x's child, and you forget to say that x is y's parent. That's the type of thing that would lead to a nil pointer issue if we were trying to go up from y to x and we didn't hit, we tried to reference y's parent and we had forgotten to update that x was y's parent. Now we have a nil pointer reference because we haven't actually pointed it at x, and we'd be in a mess there. Okay, so what's the simplest possible tree structure we can set up? It's to say every node is going to have 2 children, and so if we're at a leaf, both will be nil. All right, so if I'm at a leaf, I don't have any children, and so both of these child 1 and child 2 labels or fields are going to be equal to nil. If I'm at an internal node, they're going to point to their children. Okay, so it's a nice memory efficient way of implementing this that will show kind of what we've learned with Go in terms of pointers and methods. So we're going to do UPGMA, and the overall kind of structure of what we're going to do is going to be much simpler in main than what we've done before. So let's read in from the user. So let's take one parameter and call that the file name. And that's the only parameter I'm going to read in from the user. So it's os.args1. And after we've read in the file name from the user, well, let's read in the matrix that's contained within that file name. So remember, this function, read matrix from file, is going to return the distance matrix, and it's going to return the list of species names. And so let's call this file name with a capital N just to be consistent here. So I'm going to read in from file, and it's going to return the distance matrix and then the names of the species as a list or as a slice. Once I have the distance matrix, well, let's call UPGMA on the matrix. Let's also give it the names of the present day species. That will be helpful. And you might say, well, what is it that's going to produce? Well, it's going to produce a tree. So again, if we think about algorithms as solving a problem, and as in terms of input and output, it helps us code and understand, convert the idea contained in pseudocode or in, even before pseudocode in some high-level explanation of an algorithm to actual code. So here, what does UPGMA need to know? It needs to know the distance matrix. We're going to give it the species names too so it can label the leaves. And what does it produce? It produces a tree. All right, and so if we think in that sense, now the code should be very clear. We call UPGMA of matrix and species names. It's going to return a tree. And so I'm going to say var t tree is equal to UPGMA of that matrix. Certainly there's a shorthand, t : equal to that, but that's less precise, at least for now, than var t tree equals UPGMA of what we want to do. And so after that happens, I'm going to call t.printGraphViz. So I'm going to have a tree. A tree is a slice, so a slice is a pointer, and so tree is in some sense a pointer, but we're going to have that. We're going to call t.printGraphViz, and that's going to print out the tree in a nice format. And when you see it, you'll appreciate kind of how this works. All right. But again, what I want to focus in on is not read matrix from file, not printing the tree in a format currently, but I want to write this function UPGMA of matrix and species name. So I want a function called, I thought I'd copied it, UPGMA of matrix, which I said it is a 2D slice of floats. It's a distance matrix. All right, that's how we're thinking about it. And then the names is just a slice of strings, and it's going to return a tree. All right. I didn't provide a comment there, but I've been saying what UPGMA does, and so I think that's okay. And so here's where we take, the idea from what we had written on the level of pseudocode, and we want to convert it to Go. So how is it that UPGMA will work? It's going to take in the distance matrix and produce a tree. So if we're coding top-down, we may as well code this function first. And so let's initialize the tree, and let's give it the species names. And then down here at the bottom, we're going to return the tree. So what is it that the initialized tree function is going to do? This will create all the nodes needed and not point any node at any other node. So all the pointers are going to be nil. I'm just going to create a bunch of nodes, okay? And I'm going to label all the leaves with their associated species name. And I'm also going to initialize the clusters. And here's where it's helpful to kind of remember how it is that I thought about a cluster. And I'm going to think about a cluster as just a node. So at the beginning, all of our clusters are just the leaves. As we continue upward through the tree and join neighbors together and start to build our tree, at any given point, we have the highest level nodes are what the clusters are. So if I've joined these two nodes together, their parent is going to be the cluster, that cluster, and I'm going to throw away the two clusters at the bottom. So I'm going to go from n leaves to a single cluster at the top. And so I'm going to initialize these clusters, and I'm just going to give it t. Okay, so clusters will start out as just the leaves of t. And then the other thing to think about is, I said that a cluster is just a node, but a cluster is a pointer to a node. Okay, so now again, I'm just going to create the nodes behind the scenes one time, and then the clusters will simply point at whatever nodes we're currently considering. So at this beginning, they're just going to start off pointing it to the leaves, and every time we join two nodes together, we're going to update the clusters so that we get rid of those two and point the last element of clusters at whatever this new person is, or this new node. All right, and so because they're pointers, we don't have to create a whole set of different nodes. We don't have to do anything else. I'm just going to simply have these bookmarks, which are the clusters, pointing or referring to all of the nodes that we're interested in. So I'll initialize the tree, and then I'm going to initialize the clusters. It's just going to be a slice of node pointers. Okay, and then now for the engine, okay, we need to apply the steps of the algorithm. How many times? Well, if I have n leaves, we have n minus 1 internal nodes, and every time we're creating one internal node. So we're going to do this num leaves minus 1 steps. And so I say, what's num leaves? Num leaves is just the number of species names that we had. Okay, so however long that is the number of leaves. It's also the number of rows in the distance matrix. So we can get at this a number of different ways. And we're going to have a for loop now. So the for loop will start, let's start k. I think I used p in the pseudocode. So, or we could use p starting at num leaves. So the leaves are going to be indexed 0 up to num leaves minus 1. So we have num leaves total leaves. They're going to be 0 up to num leaves minus 1. The other nodes are going to be num leaves, so the internal nodes are going to start being indexed at num leaves, and then they're going to go up to 2 times num leaves minus 1. We won't include that, so we're going to have 2n minus 1 total, and we're going to increase p by 1 each time. So there's our for loop that's going to serve as the engine of the UPGMA algorithm. And what do? Well, first, find the minimum element of the matrix. So when we do that, we're going to find what are the row and column indices of the minimum element of the matrix, and what's the value of that minimum element. So what is the actual minimum of the matrix? So we find the minimum element of the matrix, and so we're going to get the row, column index, and the value. And I'm going to make a big assumption, which is that the column is going to be bigger than the row. That means that if you think about the matrix, the matrix, distance matrix, is going to be symmetric along that. I'm doing it in the opposite direction. If you have the matrix, it's symmetric across the main diagonal. And so if there is a single minimum, it's going to be present in 2 spots. And so for consistency and to make our coding easier, I'm going to assume that the column is bigger than the row, which means that I'm looking at something where the column, because the column is bigger, I'm in kind of the northeast part of the distance matrix. Right? So I could have a minimum value here, or it could be reflected along the main diagonal. I'm going to be looking at this one, which means that the row value is going to be smaller than whatever the column is. Okay, so they can't be equal. That would be along the main diagonal. But if I have that the column is bigger than the row, I'm going to assume that throughout the code. And so now I found the minimum element. The next step of UPGMA is, in each step, I find the minimum element of a distance matrix. Then I set the age of the current node. Okay, and the current node is going to be T of P. Okay, and its age. So if P is num leaves, this is the first internal node I'm going to consider, and so its age is equal to value over 2. So whatever the minimum element of the distance matrix is, take half of it, and that's the age of the current node. And now let's set the children of T of P. Right. And we discussed this on a pseudocode level, but we're going to be interested in considering the clusters. So child 1 is going to be clusters of row, and child 2 is clusters of call. All right. And I think this will be clear too as we implement this and as we change the clusters. So this is the hardest conceptually part of this algorithm. And now let's update the matrix and the clusters. So let's add a row and column to the matrix. And we're going to need to know a few other things. We need to know clusters, row, and call, since that's going to tell us which clusters to join into a new cluster. All right. And we're then going to add T of P to the end of clusters. All right. So the clusters are just pointers to nodes, and when we're going to create a new row and a new column of the matrix that corresponds to that cluster that I've created. And so if the matrix has n rows, then the clusters are going to start out with n elements. And so I'm going to add a row to the matrix. And what row does that matrix correspond to? It corresponds to that new node that I created. So I'm going to append to clusters T of P. All right, so T of P is what that new row of the matrix is. It's the row that corresponds to that new cluster that I created. And now hack out. So if I have a given row and a given column, we want to get rid of that row and that column and that row and that column of the distance matrix, from the distance matrix and from the clusters. So we will have matrix equals delete row and column of the matrix. The row and the column index are going to be important. And for the clusters, we're going to delete clusters of clusters, row, and col. And you will note matrix is a slice, which is a pointer. Clusters is a slice, which is a pointer, which means that we get access to matrix and clusters. And it's very tempting to just do this, right? To not return a value. I get access to matrix, I get access to clusters. But if you'll remember the issues that we saw previously, where if you start deleting elements from a matrix or from a slice, you can get into some weird behavior if you don't just return the slice. Okay, so you get some undesired behavior, I should say. And so that's what we saw previously with slices. So instead, I'm going to return these and set matrix equal to what it is that I return, and the same thing for clusters. That's the engine of the algorithm. What remains is to implement each of these functions and to see how they work. Because after this is done, n-1 times, now we're ready to return the tree. And an algorithm like this, even with excellent pseudocode and excellent planning, would never proceed as naturally as this in practice. It's important to point that out. This is kind of having already stable code and a sense of how to go through this. So in practice there would of course be pitfalls, but I want to keep this as tight as possible and to show you kind of maybe not even the best implementation, but a way of implementing this in such a way that, look at how short the UPGMA function is. Yes, it calls subroutines, right? That's a good thing. And if you take out all these comments, you have about at most a dozen lines of code that's going to actually do what UPGMA claims to do. So we can write these functions then one at a time. All right, and some of these functions are going to be trickier than others. The add row call function will be tricky. Something like find minimum element will be on the easier side, and so I think that's probably my plan for what we should do next. Or even easier, I guess, would be initializing the clusters. And I've even got my cheat sheet here so that I don't lead us way astray, and then we have a bunch of bugs that we have to figure out live. So let's look at initializing the tree. I think this is a natural way of going through it, actually, because we're going to initialize the tree first and then initialize the clusters, and it'll refresh our memory about how UPGMA works. So we're going to create all the nodes needed, and as we're not going to set any children because we don't know what they are yet. That's the whole point of the algorithm. So let's look at initialized tree, and we just need to find initialized tree. So what does it do? It takes the n names of our present day species. So it's going to take the number of leaves, not the number of leaves, but I should say the species names, and it returns a tree. And so that tree is this rooted binary tree with 2n-1 total nodes, so where n is the number of species. So let's set num leaves is equal to the length of species names. That will tell us the number of present day species. And let's also declare t, because that's what we're going to return. And again, this is nice. If we think about a slice as just a pointer, a tree type is just a slice of node pointers. So we know that the tree is a pointer itself, meaning that I don't have to worry about issues with copying or anything like that. When I return t, I'm technically returning a pointer, and so that t that gets initialized here is going to be the same tree that gets pushed around. It's being stored in one address. We're just going to have pointers to it, from all around the code, which is good. So we declare a tree, we return it. And here's where we say, okay, remember a tree is a slice of node pointers. So the tree currently is just going to be an empty slice. That's no fun. And so what we should do would be to make it, right? Remember, if we have a theorem that says if we have a binary rooted tree, you have num leaves, then you're going to have n minus 1 or num leaves minus 1 internal nodes. So we're going to make it be a slice of node pointers of length 2 times num leaves minus 1. Now, all of these pointers are nil. They have the default value of nil. And this is the type of thing that will come up, as people work with pointers for the first time or get comfortable with them, is neglecting, so thinking that if I've created a bunch of node pointers that I've done anything with them. I haven't done anything with them. They just all have default value of nil, and so we need to point them at something. And that something is nodes. And so we've made our slice of node pointers. So how we're going to do that is to say, all right, well, if I have, the tree needs to have 2n minus 1 node pointers, we need to create 2n minus 1 nodes. So let's say for I colon equal range over t. I could also just as well have said for I colon equals 0, I less than 2n minus 1, I plus plus, or we could just range it over this slice, and that's going to hit everything. All right. Let's create a node. I'm going to call it Vx, or for vertex. And so we have, let's label the first num leaves nodes with the appropriate species name. Okay, so the species names that we're going to be given are the present day species names, so they're the ones at the leaves. We won't have labels for the ancestors. So I'll say if I, remember I is the index that ranges over the whole tree, so it's going to go from 0 up to 2n minus 2. If I is less than the number of leaves, then we're at a leaf. And let's label it. So this is just by assumption. I'm going to assume that the first n, or the first num leaves, elements of the slice are in fact leaves. Let's assign its label. And so the label then of the vertex is equal to species names of I. Remember, species names just has the slice of string names corresponding to the species. So the ith one is going to be what we label the current node to be. Okay, and I could say vx.age is equal to 0.0, but it has this default value anyway. Okay, by default, the age of vertex is 0.0. Okay, and then you say, all right, well, what would I label the ancestors by? Because I don't really have, there's nothing to naturally call the ancestors. So I have n leaves at the bottom, and then let's label the ancestor nodes too. So let's have an else, all right, and let's just call it a default name, okay, or an unspecific name, because we don't have anything else better to call it. So let's label it to be equal to, I've just said ancestor species plus, and let's do a string convert integer to a string of I. So that's going to mean that if I have 10 species, the first 10 are going to be labeled by the species names, and then the next 9 are just going to be ancestor species 10, 11, 12, 13, 14, 15, 16, 17, 18. So I should probably import string convert, which has happened here. And I save this. I'm going to get a bunch of automatic compiler errors because I've got functions that haven't been defined and all kinds of issues with that. Okay, so in the meantime, we range over all the nodes of the tree. We're going to create the node at the current position. It's going to have a default age is equal to 0.0. Its children, I should put this here, and its children are nil. We're not going to update that yet. That process will happen as a result of the algorithm. But I am going to label I'm going to give it the species name label, or label it as an ancestor species. And then at the end, we want to be very careful because we have a slice of node pointers. That's the tree. Great. We've now ranged over the tree and we created a node, and it exists separately. So we have a vertex or a VX node that we've created, and it's got the appropriate label. There's just one thing to do, which is point T of I at the node that we created. And we know how to do this. We say T of I, so T is a slice of node pointers, T of I is the ith node pointer, and so if it's a node pointer, it has to point at a node, which means that it has to get the address of Vx, okay? So we create the node. This is the last we are going to see of Vx. Everything else, now that this is set, is going to be in terms of the tree T. So T, again, is a slice of node pointers. The nodes are created one time, and then we kind of ignore Vx for the rest of this algorithm. We're just going to have T. So if we want to get at the ith node, we're just going to access it with T of I, and that's going to allow us to have this bookmark to go in and find where T of I is being stored. So T has been initialized, and at the end of this, we can return the tree T. We set all the labels, and we have our nice initialized tree function here. We should have an initialized clusters function too. So it's going to be a function, we say it's a tree method. You might say, well, I want access to the tree, so I need a star there, right? Remember, we learned the difference here with rectangles and circles, where, it will create a copy of the whatever you give it, if it were a rectangle or a circle, and so you wouldn't have access to the original thing, to the original object. With the tree, you're tempted to think, oh no, I'm not going to have access to the tree, but a tree is a slice. So for some examples, you would need to do this, if a tree is an object. But for our representation, a tree is a slice of node pointers, a slice is a pointer, and so this will be handled automatically here. It's a minor point, okay? And we could actually still get at this with a slice, but with a pointer, but it's just overkill, okay? And so we have a function. It's a tree method. It's called Initialized Clusters, and it's going to return a slice of pointers. So this slice of pointers is going to be pointers to nodes. So we're going to return pointers to the leaves of the tree, which means that the clusters, if I think about it abstractly, I've mentioned this before, but the clusters are going to start off as just the leaves of our tree. And I don't want to create new nodes. I don't want anything like that. I just want to have access to those nodes. All right, so I'm just going to use a pointer to point at those nodes. So let's say the total number of nodes is equal to the length of T. Okay, and I only want to point it at the leaves. I don't want to initialize the clusters to the ancestral species either. So here's where we say, okay, if I have n leaves, then I have 2n minus 1 total nodes. But if I have n total nodes, how many leaves do I have? Here's where you have to do a little bit of algebra and get that the number of leaves is equal to the number of nodes plus 1 over 2. All right, and that looks like an integer division, but this number is always going to be even, because num nodes is equal to 2n minus 1. So you have 2n minus 1 plus 1, which is 2n over 2, and that's your n, or your number of leaves. All right, and so we're going to make our cluster slice. So we're going to have that the clusters are make a bunch of node pointers of length num leaves, right? So again, if we have an n by n matrix, we're going to have n leaves, and so we're going to start off with n clusters pointing at each of our leaves. We haven't set those clusters, but clusters of I should point to the ith leaf node of T. And so what is T of I? It's a pointer to a node. And remember that pointer to a node is just an address, which means it's an integer. So think about T of I as having a value. Clusters is also going to be a slice of integers, in a sense. It's a slice of pointers. So it's a slice of addresses. And so if I simply range over the clusters, then I'll be able to set clusters of I equal to T of I. All right. This says, look at the value in T of I. It's an address. Copy that address and set clusters of I equal to the address. And so now clusters of I points at the appropriate leaf node, which is just T of I. And so it's a nice short function because now we're ready to return those clusters. Right? It's kind of a new way of thinking about programming, in a sense, is once we move not beyond top-down programming or beyond object-oriented programming, but we start caring about the memory management and understanding how to work with pointers. This is a new way of rearranging how our brains work in order to program, in a sense. But again, to think, well, T of I is just an address, and here's where it's helpful to think about it as an address. So if I have it on the right side of an equation, that value is going to get copied, and clusters of I is going to get it. So at the end of the day, they're both going to have the same value. They're both going to point at the same node. And again, the power of this, that I just created, 2n minus 1 nodes behind the scenes, and everything will work on the level of pointers. So 2 subroutines written. We initialized the tree and we initialized the clusters. Now for the engine of UPGMA, let's look at this find minimum element function of a matrix. So we're going to take a distance matrix. I need to find it. Let's make it a little better here. It's going to take a distance matrix and it's going to return the row index, say row index, the column index, and the value corresponding to a minimum element. We're going to pass this assumption that column is bigger than row throughout this, since we could find, again, as I said, if you have a matrix and you want to find the minimum distance value, it could be on either side of the main diagonal. Okay, so it's going to be symmetric about that. And we're going to assume that column is bigger than row, meaning that we're above the main diagonal. So we're going to have a function called find minimum element that's going to take a distance matrix, and it's going to return row index, column index, and value. So that's an integer, and the values of float 64. All right. And so here's where we say, okay, I'm going to have a quick test. So if for some reason the length of the matrix is 0, or the length of whatever's in this first row is equal to 0, let's just panic, okay, and say row or column 0 rows or initial column. Okay. And it's actually helpful to know how this will work. You might say, well, what would happen if matrix of 0 doesn't exist? Well, that would be if length of matrix is equal to 0. So if there are no rows in the matrix, that would be really bad. We don't want to find the minimum element in a matrix that has no elements or no rows. And so if that's the case, we're going to panic away. You could also be the case that you do have a row, but its length, its initial length is equal to 0. We're going to panic in that circumstance either. If it's the case that you have no rows, then because this is an OR, as soon as Go sees an OR statement, it will check the first one, length of matrix. And if length of matrix is 0, it won't do this check. So it won't incorporate a runtime error by trying to access matrix of row, which is something that doesn't exist in that case. If it does exist, it'll skip this. So, we could have a long matrix with many rows, but for whatever reason, we've got a problem, and the 0th row, it doesn't have any elements in it. That would be really bad. All right. So just a brief aside there. I did this because I want to set row and column equal to 0 and 1 respectively. So this would be, and let me this isn't quite right. So this is assuming that I have that the matrix is at least 2 by 2 in order for me to do this. So I need to be less than or equal to 1 here. And this would be less than or equal to 1. Pardon the error. So it would be 1 row or 1 column. And either of those would be a bad situation. So if we have more than 1 row and more than 1 column, we can assume at this point, because we didn't hit this panic, that the matrix is at least 2 by 2. And so row of 0 and column equal 1 is the current winner. So I can access matrix of row and col. And these are the leaders, right? So these are the, I'm going to start off at, if I look at my matrix, I'm not going to look at 0, 0 because that would be a 0 value on the main diagonal of a distance matrix. That would be bad. I want to go over one element and hit row equals 0, column equal 1. And so I'm going to do a test here, but at the end I'm going to return row, col, and then the min value that I found. And we're now going to have our test, which is let's range over the matrix and see if we can do better than row, than min val. All right. So if we can beat min val, then we want to update row, col, and min val. So how do I range over the matrix? Here's it's a little exercise in ranging, which is that I want to avoid everything that's on the main diagonal or beneath it. So I want to range over all the rows, really. So let's range over all the rows. And in fact, I don't ever need to consider the last row, because the last row is going to have everything beneath the main diagonal and then an element on the main diagonal. So I'm looking at everything in the first n-1 rows. So let's have our for loop that ranges like this. And so we're ranging over all the rows, or most of them. And then for a given row, I want to go up to and past the main diagonal. So the main diagonal is everything where the row and column index is the same. 0, 0, 1, 1, 2, 2, 3, 3, 4, 4. So when I do my second ranging now, I want to start the column ranging at I plus 1, which is 1 more than the row. Okay, so that will get me to jump over the main diagonal. So if I is 0, I'm going to start it at column equal to 1. If I is 1, I'm going to start it at column equal to 2, and so on. So let's do for j colon equal to I plus 1. And now j needs to go up to the end of the row, so however long the row is, j plus plus. And now we do our test. Do we have a winner, or at least a leader? All right. If, when I test matrix of ij, if it's less than min val, then we're going to update all 3 variables. We found a leader. So we're going to say min val is equal to that matrix value, matrix of ij. And row is going to get updated to I, and col is going to get updated to j. So this is the best row and column that I've found. And I'm going to do those 2 updates and set min value as well. All right. Note that because of this, because j starts at I plus 1, it's going to go up to the length of matrix of I, it's always going to be bigger than I. It starts at I and it only gets bigger. So for that reason, col starts off here is bigger than row. Col, if it gets updated, will always be bigger than row. So col will still always be bigger than row if it gets updated. And so that's it. We've done this ranging, and at the bottom we'll return our best row found, best column, and our minimum value. There's a lot more we could add to this. We could assert that the matrix in the beginning is a square matrix. Things could go wrong if it's non-square, or if different rows have different lengths, this type of thing. That's another thing I would add that we could, append onto this later. You could write, for example, an assert square matrix function that perhaps every step through UPGMA, it makes sure that the matrix is square, and if it's not, then you could panic or something. One more little area of improvement here. We don't need to start at I equals 0 because, actually we do. So we could have something that's better, I could have something that's better in the 0th row, but, way out in some far off column. So we could wind up with a smaller value that's still in row 0, but that can beat where we are now. So I think we've covered everything that we need to cover there. And the one next thing that I would say is let's look at the UPGMA function and consider where we are. So we're getting there. We've initialized the tree. All right, we've got a bunch of nodes and they've got labels. And the first n are going to point to the leaves, and then everything else is pointing to internal nodes. We've initialized the clusters, so we have a bunch of pointers to those leaf nodes. We are ranging over all the internal nodes now, so that's where this p ranging from num leaves up to 2n minus 1 comes from. And we have found our minimum element of our matrix. We're going to set the age of the current node to be the minimum value divided by 2.0. I could be even more precise here and call it min value for consistency. We're going to set the children of T of P. So if we have a set of clusters, the clusters really will tell us what these rows are. As the distance matrix changes, what is it that the kth row of this matrix even means? Well, it's the kth cluster, which is the pointer to the current node that row of the matrix corresponds to. It's something that we discussed on the level of pseudocode before. So we'll update these two children. Now what's the next subroutine that we come to? Let's update the matrix. So we have an n by n matrix. We're going to go to n plus 1 by n plus 1, where we recompute the distance of joining two clusters together. And we have a new node. Well, what's its distance to everything else that's going to go in this new row and column of the matrix? And so we're going to take matrix. The clusters are going to be helpful, as you'll see. We have a row and a column index. Okay, so what are the two things we're going to join? We're going to join row and column. And let's write this add row call function. So again, if we're thinking modularly, I think we understand enough of what we're going to do. Now let's think about it in terms of this specific subroutine. So we're going to take the distance matrix. We're going to take the clusters, which is just a slice of node pointers. And we're going to take a row and column integer, which are the indices. Again, we're asserting that column is bigger than row. You could have a check here called assert row call, something like that, row and column that would check if and you could add this throughout, but that would simply check if we know that column should be greater than row. So if row is less than or equal to call, flip out. Okay, that's a terrible panic statement, but you get the idea. So we could do this. It's not pivotal to the algorithm, so that's why I kind of glossed over it. We are going to return the matrix that corresponds to taking, all right, we have clusters of row and clusters of call. All right, so I have the two clusters that I want to join together. So let's glue them together and form a new one and add that to the bottom row and the column of the matrix. We're not deleting anything yet. I noted that here, okay? And so at the end, down here, when we change a matrix, change a slice, we're going to return that slice down at the bottom. So that's the end here. And so distance matrix is going to be the type that we return. And so we need to return this new matrix, and we looked at this on the level of pseudocode. We said, well, let's say n is equal to the length of the matrix. As we're going through this, the matrix is getting smaller. It's not necessarily the number of leaves, it's just some number n. And then let's make some new row, all right, to be a slice of float 64s of length n plus 1. So the matrix is going to get bigger by a row, and then it'll get bigger by a column too. And all the values in that are going to be 0.0 by default. So let's set the values that need to be set. Okay, so let's have a all values 0.0 by default. Let's set the values that need to be set. Okay, for let's range over. I'm just going to use j, and I'm going to do j equals range over new row. And if j is not equal to row and j is not equal to column, so if I have found a minimum element, then that means that, well, I'm not interested in the arth cluster and I'm not interested in the seath cluster either. I don't need to set those values because that's what I'm going to glue together. Eventually I'm going to be throwing out that row and column of the distance matrix anyway. So now I will compute new row of j. Okay, and here's where it gets a little tricky. So, you know, we saw this on the level of pseudocode again. How is it that the algorithm works? Again, imagine trying to code this without fully understanding how the algorithm works. When you get into more advanced code, it becomes ridiculous. And so if we're going to do this, we think, well, remember the wrong way of doing it was to just take this raw average where we could say set, you know, wrong, new row of j is equal to, we could do something like matrix of row j plus matrix of col j divided by 2.0. So I'm going to join row and col, clusters row and col together, and I'm looking at the jth cluster in my elements. And so what's the distance from the jth cluster to this new cluster where I joined row and col together? Well, I could take the matrix value of row j, and I could take the column matrix value of col j and just average them together. That was the simple average, and so kind of that's the broke way. And the woke way is that we need a weighted average based on the number of elements in each cluster. So I need something to tell me how many elements is in cluster of row and cluster of col. If there's way more in cluster of row, then I want to pull the average more heavily in that way. If there's more in clusters of col, I want to pull it more heavily in that way, because this new distance to the jth member is going to need to be weighted based off of those two cluster elements. So I need a size 1, or I could call it size row, is count leaves in clusters of row. And size col is count leaves of clusters of col. This is another function that we considered on the level of pseudocode. It's going to be easiest to write it recursively. And if we have a strong sense of recursion, you're going to be surprised at how quick it is. But so we have size of each of these clusters. Or you could call it size 1 and size 2. And so the weighted average then is going to be to say new row of j is equal to, I'm still going to do this same idea, but now instead of saying let's look at matrix of row of j, let me multiply that by the size of however many things are in that cluster. Actually, like size 1 and size 2, it's as simple as that is. Okay, size 1 times the, so how many things are in the cluster of row, times the corresponding matrix value plus, let's weight size 2 times matrix of col j. And now we're going to divide that by the total number of elements in the two clusters together. So size 1 plus size 2, or you could call it size row and size col, because size row matches up with row there. All right. So this will compute the number of elements that we're interested in. There is one more thing here, which is size 1 is going to be an integer, and size 2 is going to be an integer, because it's just a number of elements. So for this multiplication to work out, that's a float, and this is a float. So we need to do a float 64 here as well. All right, and that should make everything work out in terms of typing. Just a little Go annoyance. We have ranged over new row. Well, it looks like a lot, but really it's just applying that weighted distance formula with my comments that are wrapping around. And so now we've set the values of new row. Let's append the new row to the matrix. That won't be too bad, right? I have an n by n matrix and I'm appending a new row to it. So matrix equals append to matrix, new row. Actually, I think this will be fun. Okay. And what we've missed out on is now we're going to have this ugly matrix that's n by n, and then it has this length n plus 1 row down here at the bottom, and we've forgotten to set all these other things. Okay, so we need to add the last column as well to the matrix. So here's where we say, all right, let's range I up to n. We don't want to go to n plus 1. We don't need to. We're just going to go up to the n rows of the matrix. And we're going to set matrix of I equal to what happens when I'm going to append to matrix of I. So matrix of I is the ith row of matrix. Append to that ith row the value that I'm interested in. The value that I'm interested in is just new row of I. That's going to keep this matrix symmetric. So I have a new row down at the bottom. And so this value needs to go here, this value needs to go here, this value goes here, and so on. So they'll pair up in that way. So this is the 0th row, it needs to get new row of 0. This is the 1th row, it needs to get new row of 1. The ith row gets new row of I. And so that will handle that. And then at the end, we return our matrix, and we're good to go. All right. And when I save that, I'm going to get some undefined functions and so on. So that's the add row and column function. It calls one subroutine, so it has our count leaves function. And the count leaves function, as you remember, on the level of pseudocode was quite straightforward. It will be on the level of code as well. So we're going to want this recursive function. Let me say it's a recursive node method that counts the number of leaves in the tree that's rooted here. So if there could be 170 leaves beneath me, or I could be at a leaf, in which case the answer is just 1. So it's a good thing I can access children. It's going to be tricky to access parents, but if I have a node and I want to know how many children, how many leaves are beneath me, I can just access the children. So let's call it, let's say, v star node, okay? And in fact, I don't need to make this, I could make this a method, yeah, it's probably fine. So I have a node pointer, and I'm going to count leaves, okay? And I actually think I wrote this, count leaves of clusters of row, so I could do it this way instead. It's count leaves of a node. And it's going to return an integer. Make that a little tighter. And so we're going to have two cases. If you're at a child, at a leaf, excuse me, return 1. So our base case would be if you check the two children, and either one of them is I'll assume it's an OR here. If you get a nil test for your children, then I'm going to return 1. kind of assumes that the children are being set correctly, that you don't have this weird case where a node has one child is nil, but the other child isn't nil. We're just going to assume that doesn't arise here. We can make our code more robust later. But so else, I don't even need an else, right? Because I'm going to return something if this is true. What am I going to return? So inductive step, count the leaves of each child. So if I hit it here, I know that v.child1 and v.child2 are not nil, which means I can access them. So remember, when I access v.child1 and v.child2, those are pointers to the children nodes and sum. So I'm going to count the leaves of each one and sum, and so I'm going to just return count leaves v.child1 plus count leaves of v.child2. I don't think I really have needed much of this other stuff, so I'm just going to make it a little wider for now. Okay, and I wound up in a different part of this code. All right, so this is the inductive step. This is the base case. We're at a leaf. And so count leaves is really, recursion can be a tricky concept to get your head around, especially because it can be so simple. That if we're at a leaf, we return 1. Otherwise, I could have, 200 leaves in this subtree and 14 in this subtree. So figure that out and add them, and then this will just recursively, go down the tree, counting leaves of each child until you hit a leaf, in which case it'll return 1, and all those will kind of flow back upward when the functions come off the stack and get returned back up until we hit the original node we started with. So we're actually not down to much. If we look back again at UPGMA, then we're going to have, here's where I start getting tired after lecturing for a bit. We've initialized our tree. Again, remember that creates the nodes, and all it does is set species names and ancestor names. It initializes the clusters, so it points n initial clusters at the leaves. Then it ranges over all the internal nodes. It does the engine, where it finds the minimum element of the matrix. It sets the age. Notice here's where your children get set. So clusters of row and clusters of col were the two things that I'm going to join together. So those are the two children of the current node. I'm going to add a row and column to the matrix, and I'm going to add, so if I've got a new row of the matrix, that's going to be the pth cluster, the pth node, and so that's my new cluster. It's just pointing at node P. So that's at the end of the clusters as well. So I have node P corresponds to the last row of the matrix now. And now I've made the matrix bigger and the clusters bigger by 1, and I'm going to throw out the parts in the interior of the matrix that I don't need anymore, which were what corresponded to clusters of row and clusters of col. So I have two little short subroutines here: delete row and column from a matrix and delete an element from the clusters. So let's write those functions. Function delete row col takes a distance matrix. It takes a row index and a col index, and it's going to return a distance matrix. Again, if we're deleting an element from a slice, we need to be careful and return something. So down here we're going to return matrix. Okay, and first let's delete the appropriate rows. So we want to do matrix equals append to, let's do everything up to col. So, and this is using the idea that if I've found that the minimum element is at, RC, it's also at CR. So if I'm deleting row R, I should be deleting row C also. If I'm deleting column C, I should be deleting column R also. Anyway, I remember that column is bigger than row. We thought, well, why does that ultimately matter? We should be consistent. And here's where we should be really careful, because if I were, for example, to delete, I wanted to delete rows 3 and 14, and I deleted row 3 first, then it would push up everything else. And so now when I deleted what I thought was row 14, I'd be deleting my former row 15. This won't happen, this issue won't happen if I delete row 14 first. And so that's the bigger index. So if I delete row 14, everything gets pushed up. Now I delete row 3, everything gets pushed up. That's fine, that's what I wanted to do. So because col is bigger, we should delete the colth row first. Okay, so I'm going to append to matrix of all the rows up to col. I'm going to look at col plus 1 and append possibly multiple rows to it. And then I'm going to do the same thing for matrix of everything up to row, and I'm going to append everything past it. Okay. And now delete columns, row, and col as well. Remembering again, we don't want to forget that col is bigger than row here. And so we're going to say for I colon equal to range over the matrix. So we're going to range over all the rows of the matrix. And I'm going to say matrix of I needs to now change. So matrix of I says, let's delete, actually, yeah, everything in matrix of I. Let's append starting at the colth element, going past it. Okay. And let's do the same thing for in row I. We're going up to the row element and everything past it as well. And now that has been updated, and so we can return our matrix. We're not down to much that we haven't defined. We're now doing the same thing for deleting the clusters. So we went to an n plus 1 by n plus 1 matrix, and then we got rid of the appropriate row and columns that we needed. So we're now back to n minus 1 by n minus 1, and we're kind of moving in the correct direction in UPGMA, because we have an n by n, we go to n minus 1 by n minus 1. Next step, we're going to go to n by n, and then n minus 2 by n minus 2. And so we're going to keep going back and forth until we get down to a small matrix, and we'll be finished. Delete clusters is going to say, let's take a slice of node pointers, call them clusters, and a row and a column index as integers. And it's going to delete the row and column index, of that clusters, and return a slice of node pointers. So the clusters are just a slice of node pointers. That's what's going to be returned. This is just a 1D slice. And so, again, we assume col is bigger than row so that I can say clusters is equal to append to everything going up to, but not including col, and then everything past col to the end. And I'm going to do the same thing for the row index. Since it's smaller, I've pushed up everything past col, and now I'm ready to do it for row. And it'd be very easy to call our work finished there, but we need to make sure that we return clusters because we said we were going to return that, and that will handle our slice issues. I'll recall that when we worked with slices in Go, I had a slice where we started with 5 elements, and then it was sitting in a larger array, and the appending caused elements to drag over, but we had an extra 5 that hung on. This won't be the problem here because you're not interested in that underlying array. You only have a slice of length of a given length. And so, for example, if I declare a slice of length n, the underlying array is going to have length n, and it's not going to be bigger in essence, right? So when we do this delete step, everything is going to be fine. The new slice, remember, is all we're really concerned about. Even if there's a ghost value that's behind the scenes in the array, we're never actually going to access that array behind the scenes, and so this will eventually get destroyed anyway. And clusters gets the right value because we're updating it when we do the append. If that didn't make perfect sense, that's fine. It was just a minor aside I wanted to clarify here. And so we're going to be good to go with this short function here. And that's it. That's everything that we had meant to write for UPGMA. I'll probably get a compiler error. I didn't define find minimum element, so maybe I named the function incorrectly. Yeah, I'd call it find min element. No need to be so lengthy. and then at line 164, I'd called something, I think, V, and then I used VX. So that's it there. Okay. So if I save that, it's not bad. I had 2 compiler errors for a couple hundred lines. Over here, when we want to run our code, we are in the UPGMA folder. I'm going to build, and everything compiled as we thought it would. And now let's run UPGMA, and let's give it a file name. So if I run it on test data set, something like, you know, this test data set that we had, test data set small 2.txt. Then of course we get a panic because the minimum column index is not bigger than row. So it's, I mean, it's a good learning experience. It's impossible. We're 2.5 hours into a lecture on this. Even after we covered it on the pseudocode level, I'm sure there's going to be some little bug that I can need to fix. So we'll have that the minimum column index not bigger than row. It doesn't sound good. Go routine. Let's see where this happened. I remember writing that panic statement. So, and we want col to be bigger. So this wasn't actually really a bug. This would be, we want col to be bigger than row. So if that's not the case, if when you do this test, you get rows bigger than or equal to col, that would be bad. Okay, so we want row less than column. Now let's compile. See if it runs this time. Index out of range. All right, so here's the next little thing to fix. So we have, let's see, main.go 27. We have line 27. That's going to be in main. Line 55, what was called here. Add row and column. Okay, so that was where that got in trouble. And then line 140 appears to be where we were out of range. Okay, so let's not get too concerned here. We ranged over the new row, and it would appear that I've accessed something here that doesn't exist. So the new row is going to have length n+1, and this one actually will be straightforward. N is the length of the matrix. n+1 is the length of the new row. And if I could get into this and print and figure out what the values are, but I've got a pretty good guess as to what the situation here is here. So we have, when we do the range over all of new row, J will range between 0 and n, because it doesn't go up to including n+1. But notice we're going to have a matrix of row J here. And J could technically be equal to n+1, and that would be really bad if matrix is, or J could be n. That would be really bad if matrix is n by n, because J would be one value too big. So I've done this ranging a little bit too long. And, you know, you'll see this by, if I print, if I wanted to figure this out, and I could be wrong, I could just be tired, but if we were to print row and J, well, I know, let me just print J. I know that I'm starting out, and here's the point of starting out with small data sets, right? So I have a 4x4 matrix, and so if J is equal to 5, I know that I'm in trouble. Or excuse me, if it's equal to 4, I know I'm in trouble. I was off by 1. Yeah, and here we are, 4, panic, runtime error, index out of range. Right, so J is J. You'll see that even a little better. It's hard to see in the midst of these runtime errors. J is 0, that was fine. J is 1, that's fine. J is 4, that's the last thing that we print before we hit this. And that's really bad. I don't want J to be 4 because I'm accessing this. So I could range over the whole new row, but the last value of new row, if you remember how this works, I'm adding a new row to the matrix. And that new row, the last element's going to be on the main diagonal. It should be a 0 anyway. So the last element will be 0 by default, which is good. And so I don't need to do this full range. I'm just going to start it at 0, j less than n, technically, j plus plus. And so now, if I build this and run, I'm going to get a lot of print statements. Yeah. So j gets printed a few times. Okay. And I'm going to, if I'd run that on a huge example, I would get so many test data sets. I always say at this point of the program, it's like the movie There Will Be Blood. There will be bugs in any code of this length, and you got to just roll with it, because I've got, you know, cheat code that I'm going off of. I've got an algorithm I've programmed from several times, and it's just being confident in your ability to find issues that you develop over time, but that, you know, a lot of it is just not panicking, especially in say a recorded lecture, and acknowledging that it's something you're going to be able to fix. If you just slow down, look at the line where something goes wrong. If it's an index out of range, listen to what it's telling you, and go from there. So it's, you know, every bug is a teachable moment in that sense. Here is what gets printed. I could print this to a file, but remember long ago in main, and this is going to be the close of the lecture, but long ago in main we had, wherever it even was, I called print graphviz. And so graphviz format, you could walk through this on your own. It just does a lot of printing in the right format. Remember, what's the edge label in UPGMA? It's whatever the age of the parent minus the age of the child is. So I get the edge labels for free. Much like with area of a rectangle, we don't need to store that as a field, because if I have this guy's age and this guy's age, I just subtract them. I get the edge weight. And so that's what this does. You'll see I have t of I.age minus t of I.child1.age, and the same thing for this. So it's ranging over the tree, and if it finds children, it's simply printing, hey, here's my label, and I'm connected to a certain child, and here's the difference in our ages. And that's what this does. Okay, so you have, this says you have digraph, means you have one directional edges, so this is going to tell the graph program one directional edges, and then here's your first edge. You print out your current species, you print out its child 1, and then you label it with the difference in their edges. You print that connected to its second child. This is the string L, and what's the difference between their ages. And if I were to take this to the program I mentioned, so we could have, I said, we could look at this on a local version of graphviz, or I could just copy this and generate a graph. Then you're going to see kind of a tree that we produce. And then we go through the process of saying, you know, is this tree correct? And that would be the next thing that we look at. So we have we have a tree here, and this is the tree that we considered last time. So we knew that the age was going to be equal to 4, and so we see that that age of 4 gets reflected. We had continued through this, and then we said, well, it's actually K and L get joined together into a single cluster here. And so the distance from I to KL is going to be 10, and that actually becomes the next thing that we compute. So the next age gets recomputed as having an age of 5. All right, so we can see here that we've got a little bit of a problem because the distance from I to KL should be 10, and somehow we've got that this distance up here has become 7.25. So we've become a little out of whack here. This distance in our previous example was equal to 1. this distance was equal to 5, and I must have put something in wrong. I don't think that it's related to the printing. I mean, it could be that. It's probably related to the construction of the tree itself. So again, this is just somewhere where we can use it as a learning opportunity and try and figure out, how is it that for this small data set, the last thing we want to do is put tens of thousands of species and then publish a research paper if we've implemented this algorithm. We should look at an example that we've done by hand and see, okay, well, we know that this should be a 1 and this should be a 5, and where we think that things might have gone astray. The problem here is probably related to the fact that we have something that worked correctly on this level. So we had a correct value of 8 here, or of minimum value of 8, and then we have a distance of 4 to our current nodes here. The age here is probably right, because you notice that it still at least has this property of being ultrametric, so that's cool. You have 4 plus 3.25 is equal to 7.25, and then you add 7.25 plus 10.25, you get 17.5. But we're a little bit wrong in terms of apparently how this age is getting set. So we know that this age is getting set incorrectly at this stage. We know that this is getting set correctly here, but we know this age should be 5. And so that's what we need to figure out. So, I will maybe cut this later, but I think that there's something we haven't said much about debugging. So let's use this as an opportunity to figure out what's wrong. And I'll just do that for however long it takes, and we'll do it. So we set the age equal to be the minimum value over 2. And so if I print that min value, we should see what the min value that it finds each time is. Okay, so here's where the visualization can be really helpful. But say I run. All right. And so, yeah, 8 gets printed out correctly, and then we're off. So we have this value of 14.5. So it appears to at least be drawing the tree correctly. It's just not computing this correctly. So we know that this minimum element may be off. All right. And so let me print as well. Let me print row and col too. Okay. Forgot a comma. And so we're at 0, 2, and 14.5. That's actually going to be the correct element of the matrix. So I actually could, after I've done this process, I could also print the matrix and just see how the matrix is getting updated. Are we finding the minimum value, for example? So here we have, after the deletion has happened, we have this matrix, and we know that that got recomputed wrong. But we went down to a 2 by 2 matrix, and everything appears to be at least moving in the right direction. We're just setting the values incorrectly, so this doesn't match what we had before. But some things are right? We have a main diagonal that looks right. Is it symmetric? It appears to be symmetric. So it's probably not related to something like when we append a new row to the matrix, we want to make sure that the other column is correct. But if you could write this out, 0, 20, 14.5, 20, 0, 22.5, 14.5, 22.5, 0, that's symmetric, this is symmetric. We could write a function to guarantee that it's symmetric, and if it ever wasn't, then we could throw an error or panic. That's another direction we could go. Next thing is, does it actually find the minimum element? Well, 14.5 looks like the minimum element here to me, so that function might presumably be working correctly. Here's a 2 by 2 matrix, 0, 35, 35, 0. That's the correct row and column. Column is bigger than row, so we're good. And it's the correct min value here. So, it looks like things have gone wrong here when we recomputed, or we came up with the new matrix. And so let's see, all right, kind of everything is on track there, but I've printed out row, column, min, val. And let's print out after we add. So after we have added a new row and col, let me print out the matrix this time. So now the matrix will be a little bigger. And let's take a look at it here. All right, so that's a little bigger. And I need to probably print the matrix in a nice form. But yes, so it would appear to be that this last row is being computed incorrectly. So we're on a really good line here because, you know, if you look at the other elements, you could think that maybe the other elements are getting affected. We have our 4x4 matrix here, and it appears to be okay. It's not like I overwrote anything. I just have new row is wrong, right? So you have 14.5, 22.5, 0, 0, 0. This new row is wrong, so the whole matrix is going to get thrown off after the first step. So we keep getting there. You know, we're solving this mystery. We're not panicking. We assume that if we just print enough stuff or take a look at what's going on, we'll get there. I must have written the, you know, we've diagnosed that it's probably in add row and col. So I need to go into add row and col, and I need to just figure this out. All right, so we've made our new row, we've ranged over it, and we only want to set the values from j to n, j++, that looks good too. Okay, we counted the number of leaves. We could count this too. Print f size 1 and size 2. If we know our example, then we should know how many things are there. So we have, you know, one element in each. So this seems like it might not be ideal. So we have 1, 1 is the first thing that gets printed, and so that's good. But the next thing that we do is 1, 1, 1, and K and L have been joined together, and then, you know, that winds up being the minimum element. So it would actually appear that the size, the number of leaves beneath this might be off. Okay, so let me print the clusters each time. Maybe the clusters are wrong. This is going to give me some weird output, I think. Yeah, so it's going to give me a list of clusters, which is just the node addresses, which is not ideal here. So I think this is probably okay. If I have to get into this, we'll be in trouble, but I just have the intuition that we've got some issue with the weighted matrix computation, and that's the easiest thing to check. So let's make sure that when I recompute, I set size 1 is equal to count leaves, size 2 is equal to count leaves. If it's not this, we'll just have to tear it apart and test this thing one function at a time from the bottom up. But and here it is. All right, so you've got I did the float 64 as size 1 times the matrix of row j. Great, and I added that. Order of operations. So, you know, we get killed by our 7th grade algebra teacher because we forgot to do that first. And so when we did this division, we had, you know, this float 64, and then it was getting divided. So let's see what happens. All right, and this is starting to look good. So we got a small test case. Let's come back to what we had before. copy it in, and all right, now we can celebrate because we've got a test case that appears to be working. That's the function that, or the tree that we produced before, where we have, you know, a match of our test case. Does this mean that we're 100% finished? No, it doesn't, because we could screw this up on a slightly larger example. So you would want, or a different small example. So you want to test this on multiple examples in order to verify that we think we're on the right track. This is a good first step though. And I think we're probably in good shape. And so I'm going to be confident enough to run this. We've already compiled it. I'm going to change what we run this on to ebolavirus.matrix.txt. All right, and yes, this should be written to a file probably in practice, but you know, this is just a quick way of showing it without making this a class about data viz. And so I can generate the graph. And so the question mark is what we didn't know. And so again, this is just the same gene sampled from a bunch of species, and each one is labeled by the initial source of that species. So you had kind of a Central Africa original strain of Ebola virus, and you have a different spot of a Bundibugyo that was taken from Uganda or DRC. Then you have Ivory Coast, which is Typhorus, which is actually near where that 2014 outbreak happened. So that was our initial hypothesis, that they would be neighbors in this tree. It's not the case. And then we have things that are farther to the east, Reston virus and Sudan virus, in terms of where they were initially discovered. So we don't have a picture that reflects geography. We have an outbreak of Ebola from a strain that was originally found in Central Africa that just pops up in Western Africa. And especially if you look at the weights here, you know, these weights are small, and so you have a small distance here, and you have bigger distances if you go anywhere else, because you have a 15.83 and a 15.68. And you know, a pointer to some of my bioinformatics courses with Pavel Pevsner would be to say, if you're interested in where would we get, you know, these original distance matrix values to begin with, where we're trying to match up or approximately match up the distance matrix to the tree that we produce. Well, that's an entire like collection of weeks of material that you can delve into if you're interested in that. But for now, I'll just point out that, say, if we get the distance matrix for free, here's what UPGMA gives us. And the picture that it's painting is that, you know, these Ebola virus species are clustering together really well, but there is some differentiation, and that might actually be really helpful too. So this looks like a classical Ebola virus that pops up in West Africa. And so we have two questions. One, what caused that? All right. And the kind of high-level answer is, well, there's a reservoir for this virus that's non-human, that the virus is existing all the time and mutating and living in its own kind of ecosystem, and that's probably in bats or in other creatures. And then you have, you know, that the bats themselves can travel throughout Africa, and you have crossover points where sometimes the virus jumps from a reservoir into humans. All right. And I think that's widely believed to have been the case in the 2014 outbreak. Then the next question you could have would be, you know, how rapidly are these things changing? So, you know, even within a human outbreak, how quickly is the virus mutating as it's jumping from human to human? And how could we perhaps use that to treat people? That, for the 2014 outbreak, that type of real-time genome sequencing of a virus was, I think, a landmark example of trying to do this at scale during an outbreak. Of capturing a virus in a bunch of different individuals and seeing how, after it had translated over to humans, the virus itself was changing over time. That's such a really cool thing about kind of the frontier of research in biology, and that the amazing amount of kind of the computational side of what becomes like the response to a crisis, a viral crisis and an outbreak, is to, you know, get a bunch of people to sequence some genomes and run algorithms. Like, nothing could be cooler about our field than that it's fully transformed in this sense in terms of how we can respond to it as well. So just an aside about bioinformatics and computational biology as we analyze this. Yes, it's a primitive picture, so find some cooler data visualization and feel free to plug it into that. But for now, I'll leave you with that. And it was a lengthy lecture, but we learned a lot. We saw a lot of object-oriented programming. We saw how Go implements methods and pointers and why pointers can be important, why we care about how memory gets managed. And then we saw that in practice where, for example, for UPGMA, we created a bunch of nodes exactly one time, and then we had clusters that referred to the nodes. We had a tree that pointed at the nodes, and we let all those pointers just kind of exist and communicate with these nodes that we created, which were kind of living behind the scenes. So, and then at the end, of course, we saw a big program is going to have bugs. We can not panic and just take a look at what's working, what's not working, where does it break, and so on. And so that was a lengthy one, but a lot of fun. And thank you for joining me. And until next time, I hope to see you then.